In this lesson, we're going to begin the discussion of calculating derivatives directly. We'll start with powers and polynomials. This first definition is not something that will be tested, nor is it really in the textbook. But this is the definition of the derivative that is often used in a higher level calculus course. But the reason I show you this is not so much that I expect you to use it, but I want you to see where it's coming from, because this formula is used to prove a lot of the facts that I'll show you in this lesson. Basically, if you recall, we were using a 0.001 when we estimated a derivative. We basically took the point where we were going, added 0.001 to it, and plugged that into the function. Then we subtracted the function value at the original point and then divided by what ended up being 0.001. So the idea for the derivative is the same idea. You would take this delta x, which is your increment, and just like when I mentioned the 0.1, the 0.01, the 0.001, you would keep shrinking this and shrinking this down, and this is that limit process I had talked about. Keep shrinking the increment and look for a pattern. That pattern is what will actually give us our answer as to what the derivative is. If we wanted to actually use this, which could potentially show up on, say, a bonus question, what you would do is start out by just plugging everything in with the delta x and the x's, and try to simplify as much as possible. If you do this right, this tends to have a place where all the terms that don't have a delta x in them cancel out, and then you can cancel that delta x with the one in the denominator, and then basically plug in delta x equals 0. That's a strategy that works well for these. So with that said, everything that we talk about today is actually related to this in that it can be proven, but you won't need to use it directly. First off, let's pay attention to the fact that derivative and slope were the same idea. So remember, a function that looks like f of x equals k is a horizontal line. So for any number, if you want to take the derivative of any number, a horizontal line has slope 0. So that's your first rule. The derivative of a constant would always be 0. Next, if you're looking at a linear function, b plus mx, well, the slope of that function is m. And in particular, the function x, the slope of that function would be 1, and that's the rule that I would like to highlight. The derivative of x is 1. So for a quick example, find the derivative of 2016. Well, 2016 is a number, so the answer is just 0. The derivative of any number is 0. Find the derivative of this linear function, 3 minus 2/5 x. Now for the first problem, I use this d by dx notation. For the second one, let's give it a name, f prime of x. It would just be the slope here, and the slope of this line is negative 2/5. Here's something we can combine with what we've talked about so far. When you're talking about a constant multiple, if you have the derivative of a function times a constant multiple, then you can take that constant multiple times the derivative. In other words, when you have a coefficient of some kind, you can ignore that coefficient and take the derivative of the variable part. We'll talk about that more as we go. But I want to give you a little idea as to why this works. Imagine this original picture where this is the slope at some given tangent line. If you were to multiply this function by 3, which would multiply all the y values by 3, you'd get a graph that looks like this. And notice that in this first setup, this tangent line is actually 3 times steeper than the original tangent line. Similarly, if you divide the function by 2, basically dividing all the y values by 2, the new slope is half as steep as the original. If you multiply by a negative number, it flips the function over, and the 2 would also make a difference here. So when I switch the 2 and flip it over, it becomes twice as steep and is actually the opposite steepness. So this is just a justification that when you multiply a function by a constant, the slopes are multiplied by the same constant. Therefore, the derivative of a constant times the function is the constant times the derivative. This is a fact that I don't necessarily need to put in a box. It's something you'll learn to do intuitively. It also turns out that the derivative of a sum or difference is the sum or difference of the derivatives. You can take the derivatives term by term. And just to give you a little picture of where this comes from and why this works, let's do a couple of quick average rates of change to represent the derivative. So for f of x, I'm going to do 15 minus 13. over 2 times 1, and I get 2. For g of x, I'll do 5.3 minus 4.2 over 2 minus 1, and I get 1.1. Now for f of x plus g of x, if I were to add these together, I get 17.2 and 20.3. So if I calculate that average rate of change, 20.3 minus 17.2 over 2 minus 1, notice I get 3.1. And the key here is that I took the average rate of changes separately, or I added the functions together first and then took the average rate of change. But notice that this number plus this number taken separately is equal to this number that was done second. Here's the first big rule for derivatives, the power rule. The power rule is how you take the derivative of any power, and to show that this works, you need to use that definition from the first slide. So we're just going to learn how to use it. This is a very useful derivative rule in general. So how you use the power rule is you take your power, bring it to the front, and then subtract 1 from the power. Again, bring the power to the front, then subtract 1 from the power. Let's do a couple of examples. F prime of x. I'm going to take my power of 7 and bring it to the front. That gives me a 7x to the, subtract 1 from the power, and I get 6. Next one. Same thing, I'll take the 9 to the front. That gives me g prime of t, would be 9t, and then remember, subtract 1 from your power, and you get 8. So the power rule is a one-step process that you'll want to learn to do in one step. It changes a little bit when you have a coefficient in terms of how the one step works, but we'll talk about that momentarily. How about some other types? What if these are not necessarily just single whole powers? Well, for all of these, you'll want to do what we call a rewrite step each time. So for 1 over x to the fourth, remember from your rules of exponents, that's the same as x to the negative 4. This is necessary to get these right every time. You need to rewrite these. So I have y prime is equal to, bring the negative 4 to the front, and then I'm going to write this out to subtract 1 from the power. When you're doing a negative number, be careful. It's very easy to make a mistake here, and there's no shame in pulling out a calculator to figure out what negative 4 minus 1 is if you must. I get negative 4 x to the negative 5, and then I'll rewrite that as negative 4 over x to the 5th to change it back to the form it was originally in. All right, what about the square root of x? Well, the power associated with square root of x is x to the 1/2. So then for y prime, I'm going to bring the 1/2 to the front, and then take 1/2 minus 1. So that gives me 1/2 x to the negative 1/2. And then let's just keep going with this. I'll take the 1/2 power to the denominator and make it positive, and then I'll change that back to a square root. So this is my final answer, but there's one more thing I want to say about this problem. This is not a main derivative rule, but it comes up so often that I like to write it as an actual rule that you want to learn. I'll be using this shortcut frequently throughout the course, so it's a great idea to internalize this one. Every time you see a square root of x, this is just a quick rule. It doesn't apply to any other roots or really anything else, but it just comes up enough that it's worth doing. And then finally, if we have a decimal, it'll be much the same. 3.5, t to the subtract 1, and you get 2.5. And I'll just leave that one exactly as it is. Now that we have these various rules, we can actually take the derivative of any polynomial. Let me demonstrate how. So for this one, we have f prime of t. And remember, a constant multiple is one that we just leave in front, and then we'll take the derivative of the variable part. So leave the 2 in front, and consider the t to the 5th. I'll bring the power to the front, and then subtract 1 from the power. And so then what I would do to finish this is multiply 2 times 5 and get 10 t to the 4th. Now, one thing that I would like everybody to learn how to do is to do this in one step. Basically, when you bring the 5 to the front, if there's a coefficient, multiply it by that coefficient, and still subtract 1 from your power. So if I bring 5 to the front and multiply it by 2, I get 10, and then t to the fourth. You'll want to get into the habit of doing that very soon. So how about r of t here? Well, r prime of t. Remember, if you have two terms like this, you can take care of it term by term. We'll just keep the minus, or if there was a plus, we would keep that where it is. T to the fifth, bring the power to the front, subtract 1 from your power. T cubed, bring the 3 to the front, subtract 1 from your power. And we have a quick, easy answer. So if you have sums and differences, you can take it term by term. And if you have coefficients in front, you can leave them in front, or better yet, go ahead and multiply when you bring the power to the front. Let's do a couple more examples. For this one, f prime of x, I'll show you out the rules here. I would have the 10 sitting in front, but if you want to, when you bring the 12 to the front, go ahead and multiply. 12 to the front, subtract 1 from your power. Now, the 13x, this is another one I want you to get into the habit of a shortcut. I told you that the derivative of x is 1. So that's an important rule to keep. Here, I'll have 120 x to the 11. But what I also want to point out is for the 13. I got 13 times 1 is 13, but there's a shortcut here also. Anytime you see a number times x, the derivative will just be that number. So we end up with just a 13, and you could do that in one step as well. For this next one, let me rewrite this as 1/6 t squared plus 7. I don't necessarily have to do it that way, but I wanted to show it to you this way so that you can see that that over 6 is nothing more than a coefficient. So then when I take g prime of t, I get 1/6 derivative of t squared would be 2t. And remember, the derivative of a constant is 0. So now I'll take the 1/6 times the 2 and get 1/3 in t. But I do want to show you one other approach. Another way you can do it is just remember that the over 6 is part of a coefficient. So just take the derivative of t squared directly to get 2t. Still got the over 6, and the plus 7 would go away. If you did it that way, you would get t over 3, which is honestly a slightly more consistent answer with how the problem looked from the get-go as well. Now let's start looking at a few different applications of this. Remember, the derivative gives the slope of the tangent line. So now we can find the actual answer to the equation of the tangent line. So let's do this for the function x cubed plus 4x squared minus 7x plus 12, evaluated at x equals 1. So we want the tangent line at this point right here. To do a tangent line, it's actually a three-step process. First off, you want to know the slope of the tangent line. To get there, let's take the derivative. So we'll start off with calculating y prime using the rules we have just started talking about. For x cubed, bring the 3 to the front and subtract 1 from your power. Now I want to go ahead and mention the shortcut. We're going to bring the 2 to the front, but when I bring the 2 to the front, I'm going to go ahead and do 4 times 2 is 8. Then when I subtract 1 from my power, I just have x. The minus 7x, like I said, any number times x will just leave the number. And the plus 12, that's a constant, so it's just going to go away. Now to find the slope, I'm going to take my m to be the value of the derivative when I plug in 1. So I'm going to plug 1 into this derivative that I just found. When I do that, I get 4 for the slope of the tangent line. That's step 1. For step 2, I want to know the point that the tangent line goes through. I'm only given x equals 1, so if I want to find the y-coordinate, let's plug it into the original function. If I do that, I get 10 for my y-coordinate. So that gives us a point that is on the line, and that's something I need to find the equation of the line. The point is 1, 10. The final step is to use your point-slope formula. Remember, it's y minus your y-coordinate that I'm getting from the point is equal to the slope times x minus your x-coordinate from the point, or what was given. So let's distribute the 4. That gives me y minus 10 is 4x minus 4. Add 10 to both sides, and I get that the equation of the line would be y equals 4x plus 6. So that's a three-step process for a tangent line. 1, find the slope, 2, find the point, and 3, find the equation of the line. And since I have this nice graph here, let's go ahead and point out the y-intercept would be 6, and we can try to draw the equation of the line. So that's the equation of the tangent line and the graph of the tangent line, and now we actually have a really clean picture of what that looks like. Since we know how to take one derivative, we can also take the second derivative. So let's go through that. F prime of x, when we have x squared, would be 2x. F double prime of x then would be the derivative of 2x, which is 2. Now remember, the second derivative talks about the concavity. But the second derivative is just 2. That's always positive. So if the second derivative is always positive, the function is always concave up. So it's concave up on the whole real number line, and it might be meaningful just to draw the function, f of x equals x squared. Notice that this graph is indeed concave up on its whole domain. Let's do the next one. G prime of x would be 3x squared. And then g double prime of x, remember when you bring the 2 to the front, multiply it by the 3 that's already there. That gives us 6, and then x to the 1 is what remains. Now this one, I'll go ahead and draw first. You'll notice that the graph of x cubed does indeed switch concavity at 0, and if you look at the second derivative, that's exactly what's going on. If x is positive, the second derivative is positive, which is why the function would be concave up. If x is negative, the second derivative is negative, and that makes the function concave down. So here's what that looks like written down. Now that we have a derivative, remember another form of the derivative is the idea of marginal. So let's talk about marginal since we can take a derivative directly. The revenue from producing q units of a product would be 900q minus 4q squared. Now the first part of the question is just asking about putting r of 100, so let's plug that in. If I plug in 100, I get $50,000, and that is a total revenue. So for our interpretation, if 100 units are sold, the revenue would be $50,000. That's pretty standard from what we've run across. Now for r prime, you might recall that the derivative of the revenue is the marginal revenue. So let's calculate this derivative. Now we're taking the derivative with respect to q, but it works the same way. 900 times the variable is just going to leave you with 900. And then the 2 needs to come to the front. Again, you'll multiply it by the 4 and you'll get 8q. Then let's plug 100 into this. When I plug 100 into this, I get $100, but this is actually dollars per unit. Because remember, the derivative is always the units of the function over the units of the variable. And finally, to talk about the interpretation of this, remember the derivative, or the marginal, as however you would like to look at it, is always the concept of next. So we're talking about the 101st unit here. The 101st unit would bring in an additional $100 of revenue. The next one, if you will. For this last example, this is going to involve some of the nice graphing things that we talked about before. I may have mentioned that when you take the derivative of a function, it tends to drop by 1 degree. Now I can explain that a little bit better. So let's consider a cubic function, and let's find its derivative first and foremost. So y prime, let's be careful on this one. The derivative of x cubed is 3x squared, and I just left the a in front. The derivative of x squared is 2x, and I just left the b in front. The derivative of cx is c, and d would disappear. So if I was to simplify this, I'll write it as 3a x squared plus 2bx plus c. So a cubic function becomes a quadratic derivative. And that's true in general. You can probably see how no matter what I start with, when I reduce the degree by 1 from taking the derivative, that reduces the degree by 1 for the actual whole function. Let's make a random respective cubic. Let's suppose this was our cubic function. Then if we were to try to draw the derivative, we would find the max and the min, and those locations would correspond to zeros on the derivative graph. Then we would look at where the function is increasing and decreasing. It's increasing before and after, and it's decreasing in the middle. Wherever the function is decreasing, we have a derivative being below the axis, and wherever the function is increasing, the derivative is above the x-axis. So also, we would expect this to look like a quadratic just from the graphing things we talked about previously. And here's the general rule. The graph of the derivative of a polynomial will always look 1 degree lower.